Hello guys, nice to see you. Hope you had a nice fall break and relaxed a bit.
Good afternoon.
Hi.
Excuse me, Professor.
Yes.
I wanted to clarify, are we going to start the new chapter of chapter 13 today?
Yeah, it's gravity.
Okay, thank you.
Yeah, today we will discuss gravity and we'll discuss the Newton's gravity law and also go to Kepler's law to clarify what they are and provide some physical background of these laws. So what's the physical origin and reason for that? Empirical laws. And go on with gravitation related chapter, like topic. I guess for all this week we will work with gravity. Kind of interesting topic. Okay, so I guess people can join us on the way, those who hasn't yet done that. And let me try to switch. So as we already mentioned, so today we're going to start a new topic, which is gravity. And based on what we have already learned, we know that there are forces and interaction between bodies. We understand which kind of laws they follow. We have 3 laws of motion. We also know kinematics, so we can, if we know forces, we can predict where and how these bodies of our interest will move and where they will be located in space over some time interval. So until now, we didn't really consider the origin of these forces and just claim that, okay, there is a force and exerted on this body. However, also really matters to understand the nature of forces, and there are different types of forces. We'll not go too deep in this discussion, but 2 types of forces define macroscopical world which we experience like in everyday life. This is gravitational and electrodynamic, like electrostatic and magnetic interaction. So today we are going to focus our attention on gravitational interaction, and of course the biggest contribution was made by Newton. We all know the universal gravity law derived by Newton, and it's not so straightforward how he came up with this point, with this statement of the law. We will consider it in more details after being familiar with Kepler's law, because they were fast. So Kepler's laws are based on astronomical observations, which were done earlier before the law of gravitation was derived. And based on these findings, like some empirical means experimental, what we observe based on this empirical data, and analysis of this. Finally, the law of gravity, universal gravity law, was derived. So if we consider, for instance, a system of Earth and Moon, so based on the first law of motion, which states that if there is no force acting on a body, so we have some inertial system of coordinates, and external forces are compensated or they're equal to zero, body should move along straight line without any acceleration with constant velocity. So observing the motion of Moon about Earth, we understand that definitely there is some force which keeps this Moon close to the Earth. Otherwise, it would just go like move along the straight line with constant velocity and away from Earth. It wouldn't stay here. From the other side, according to the third law of motion, if there is some force exerted on the Moon from the side of Earth, means Moon exerts the same by magnitude force, but in opposite direction, and acts to the Earth in the same way. So there is some fundamental interaction between two masses, like two bodies with some certain masses, and the law of gravity gives us the quantitative description of this relationship. So let us change the screen. Oops. Yeah. And we can, so in 1687, quite a long time ago, Newton published his work, like some paper, Mathematical Principles of Natural Philosophy. And there he, for the first time, presented the result of his work, which was, as a result, was the description of gravitational force, interaction between two bodies. So that looks something like this. We have some force of like gravity equal to capital G, m1 times m2 divided by r squared. So here we have this capital G is constant. It's so-called gravitational constant, and it's equal to 6.674 10 to minus 11. And in units, it will be Newton square meters divided by kilograms square. So this value of this constant was obtained experimentally later. We will mention about this a bit later. But what is interesting, the main conclusion from this equation, first of all, the interaction, gravitational interaction between two bodies is proportional to the masses of these bodies. So we have product of m1 and m2, and reversely proportional to the square root of distance between bodies. So gravitational interaction decays quite rapidly with increase of the distance between bodies. So as you see, we don't have vectors here. So if we want to write the this gravitational law in vector form, so usually it's done in this way. So in that case, we need to be more specific. Let's say we have, we have body 1 and body 2. So then force which will be exerted on body 2 from the side of body 1 will be F12 vector will be equal to minus capital G product of M1, M2 divided by R squared. And here we have a unit vector, which is directed along the radius vector. So it's like unit radius vector. It gives us the direction. And unit radius vector is directed along the radius vector, which goes from body 1 to body 2. And since body 1 attracts body 2, the gravitational force will be in the same direction, but along the same direction, but in the opposite way. So it will be, that's why we have this minus in front of equation. So this is vector form of this equation, and the most common, like natural to start discussing this gravitational interaction is to start with examples which are kind of what we experience in our everyday life. So we deal with gravitational attraction of Earth, which acts on all bodies on its surface and on us as well. So we can write that the gravitational force on the surface of the Earth will be equal to capital J mass of the Earth times mass of any object body on its surface divided by radius of the Earth. So what this equation tells us, in solving some problems where you want to calculate the gravitational force on the surface of the Earth or any other planet, it's possible to consider, instead of this huge sphere with some distribution of mass in volume, it is possible to consider just mathematical point with mass of the total mass of the planet, which is located in the center of the Earth or any other planet. So here we consider actually, then if we go for this model, we have this point which is in the center of the mass, center of the Earth with mass of the whole planet, and then this capital R, which is the radius of the Earth. It will be the distance from this center where all mass is located to our object, which is located on the surface of the Earth. So that is good approximation and easy to deal, which doesn't require to consider some distributed mass all over a big volume. So we know that at the Earth's surface, we and also any other objects possess some weight. And from previous material which we were working with, we know that weight is defined as the product of mass and g, which is acceleration of free fall. So this weight is nothing else as the gravitational force which acts on the bodies on the surface of the Earth. Then it will be equal to this gravitational force. We can write capital G, mass of the Earth, mass of our object divided by radius of the Earth square. And from here, we can cancel out mass of the object. We get equation for the G, for the acceleration of free fall, which is equal to the gravitational constant times mass of the Earth in our case, or any other planet, and divided by the square root of by the radius in second power of this planet or Earth. So that is the origin of this free fall acceleration. And if you substitute here values for mass of the Earth and radius of the Earth, taking into account value for the gravitational constant, you will end up with this well-known value of 9.8. Again, it's considered to be uniform all over the Earth's surface. However, as we mentioned earlier, because of the deviation from the ideal sphere, the acceleration of free fall is a bit larger on the equator. However, it's not so essential. So now let us consider what happens if we go a bit higher. What if we move upwards from the surface of the Earth? So then force, gravitational force, will be equal to the, like we have this gravitational constant, again, mass of the Earth times mass of the object. And here it will be radius of the Earth plus the height, the distance from the surface to that position where we locate this object, square. And at the same time, we can write that this is equal to the weight of the object and this height. It will be m times g as a function of h. So g is not a constant. It changes, depends on the location. So on the surface of the Earth, it's 9.8. But if we move away from the planet, it will decrease. And now we can even get, if we cancel out this mass, so we get a equation which describes this dependence of g on height. So it's actually this one. So let us consider one example, which is our International Space Station. So we know that radius of the Earth. Excuse me? Do you have any question? Okay, never mind. So we know that the radius of the Earth is about roughly 6,400 kilometers. And the height of the orbit of the International Space Station, h, is something about 350 kilometers. It's not important to be very accurate. we just want to compare these values. And we see that radius of the Earth is much larger than the height of the orbit. So we had this equation for the acceleration of free fall as a function of h, of height. So g as a function of h is equal, so what did we have there? It's acceleration of, it's constant, gravitational constant times Earth's mass divided by the sum of Earth's radius and the height of the orbit. And this is in second power. So we don't go for calculations. It's not important to get the number. We just need to understand the concept, the idea that acceleration of free fall at this height where International Space Station is located will be not much different from the acceleration of free fall on the Earth's surface. So why? Because here we have a huge number plus small number. So if we have this small number or we don't have it, it will not be a big influence on the result. So the dominant factor here is the larger value, much larger value, and this is Earth's radius. So it will be like maybe 10%, just 10% less than on the surface of the Earth. However, you see that the astronauts and other like objects in the International Space Station, they don't experience gravity. They are flying in and these water drops are making some spheres in air, so they don't experience some gravitational force. And that happens not because sometimes people make a mistake that consider that it's because the station is in the space and it's far away from the Earth. That's why gravitational field is kind of low there and you can neglect with it. It's not true absolutely. So you know that it will be maybe 10%, just 10% less than on the Earth's surface. However, astronauts on the International Space Station experience permanent free fall. And they just don't reach the surface of the Earth because of their high velocity, like high speed, and also high location on the above surface of the Earth. But they always continue to experience these free falling conditions, and that's why they experience don't experience presence of gravity and behave like gravity is compensated. However, indeed, at this location, the acceleration of free fall is not much different from that one which we experience on the surface of the Earth. So another interesting case to mention is application of this law of universal gravity to determine density of the Earth, for instance. So again, we come back to this equation for the acceleration of free fall on the surface of the Earth. So it will be the same as the previous one, just without h. Yeah, and we know that density of the Earth or any other object, it's mass of this object divided by volume of this object. So volume of a sphere, so our planet is a sphere pretty much, can be defined as mass of the Earth divided by 4 divided by 3 p r cubed. This is radius of the Earth. So we can now define the mass of the Earth from this equation and calculate the density. So it will be like mass of the Earth is equal to the product of acceleration of free fall to the radius square divided by capital G, which is gravitational constant. And from here, density of the Earth is GRE square divided by capital G 4 divided by 3 PRE cube. So we can cancel out this and this, and we end up with 3 divided by 4 acceleration of free fall on the surface of the Earth divided by pi capital G constant, gravitational constant, times R E, radius of the Earth. Yeah, so this is the way how you can get the density of the planet, which is not, from first point of view, not so trivial task, but definitely it's some average density because the mass in the Earth is not uniformly distributed, but some average density of the planet can be obtained from application of the universal gravity law. So now let us ask one question, and this is question: how do we come to this law? Because so far I didn't mention you how it was derived, so I just provide you with the law itself with some equation and tell you, okay, this is the truth. However, to come to this point, it should be based on something. And if you indeed believe that Newton came to this point because the apple was too heavy or the tree was too high, that is not true. Definitely he had to use some already existing information to base as a basement for the derivation of this law. And for that purpose, definitely Kepler's laws, like 3 Kepler's laws, they were served as a basement. So we definitely need to go through them, and besides giving the definition of each law, try to understand the physics behind it. So why this law is working like this, in this way, or not in another. So a little bit of history. So long time ago, in 1543, Nicholas Copernicus proposed so-called heliocentric model of our universe. So before that, starting from some Greek philosophers, it was dominated geocentric model. So people considered that all objects in the space are rotating about Earth, which is located in the center. You cannot judge them for such ideas because from the first point of view, if you are not very attentive, it looks like that sun is, by perception, it looks like that sun is rotating about Earth, not in the contrary. However, based on more like observations and thorough analysis of what people actually see, Nicholas Copernicus proposes heliocentric model that the sun is located in the center of our solar system, and the Earth and all other planets are rotating around the sun. So that was already a groundbreaking achievement of realizing this concept. Then later, Tycho Brahe organized some detailed astronomical observation of all planets visible with naked eye. At that point, the telescope was not, hasn't been yet invented. So only those planets which are seen with naked eye. He was observing how these planets are moving with respect to stars, like hundreds of different stars, which are considered to be not very far away from us. And that's why you can see the motion of planets with respect to these stars. And he had an assistant who was actually Kepler. It took 16 years for Kepler to analyze this empirical data. Like, empirical means that what you observe, what you get from experiment by observation. He, after 16 years of trying to analyze it, developed some 3 laws which can be applied to every planet in the observed planet. At that time, it were not all planets which we know nowadays, but only those who were, it was possible to observe with naked eye. By the way, do you have an idea which planets can be observed with naked eye without any binocular or telescope? Can you give some examples?
The moon.
I mean, that is true, but that is not a planet, that is a satellite.
Maybe Jupiter?
Yeah, Jupiter is the largest planet in our solar system, and you definitely can see it with bare eye. Some people even claim they can see satellites of Jupiter with naked eye, which is insane, but I'm not sure that there are many of those. So, but Jupiter for sure you can see. Venus is the brightest planet. You can see it either shortly before sunrise or shortly after sunset, because it's located quite close to the sun. Then Mars and Saturn. These planets can be seen with naked eye, at least average naked eye. I'm not sure about some extreme cases. So, based on these experimental observations, 3 laws of Kepler's laws were formulated. So first law is that all planets move in some elliptical orbit with the sun located in one of the focus of this ellipse. And keep in mind that circle is some specific case of ellipse, but we will discuss this in more details a bit. Then second law, Kepler's law, is that radius vector drawn from the sun to the planet sweeps out equal areas in the same time interval. So means that the area which is swept by radius vector doesn't matter where planet is located on this elliptic orbit. For every given interval of time, will sweep the equal area on this like projection of the elliptic orbit. And the third law, Kepler's law, is the square of the orbital period, so the time it takes to make one revolution, like about the Earth, about the Sun. So the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. So if this will become a bit more clear when we discuss already a bit more about first Kepler's law. So let's come back to the first Kepler's law and provide some information which is necessary to understand better all Kepler's law. Specifically, define what is ellipse and give some information on its parameters. So the first Kepler's law states that all planets are moving around the sun. They follow some elliptic orbits, and in one of the focus of this orbit, the sun is located. So for those who doesn't know, ellipse looks like this, and by definition, ellipse is the set system of geometrical points, like here on this ellipse shape. So it's a system of geometrical point when the sum of distances of each of these points to the focuses of the ellipse, let's call it focus 1, focus 2, is a constant value. So if, for instance, we measure distance from F1 to O and from O to F2, this distance will be equal to the sum of distances, for instance, let's call it O prime, between point F1 to O prime, from O prime to F2. So this is definition of ellipse. And ellipse also has some parameters. It has this major axis. So here we have some center of ellipse. This distance from the center to the edge is called A, which is semi-major axis. the smaller distance from the center to the edge of to the ellipse shape is called B, which is minor or a semi-minor axis, and the distance between the center and the focus here is C. So there is a parameter which is called eccentricity of ellipse, and this is defined as E equal to the ratio between C, so this distance of the focus location from the center of ellipse, to the A, which is the semi-major axis of ellipse. So as I mentioned earlier, circle is a specific case of ellipse because in case of the circle, two focuses, they are located in the center, so C is equal to 0, and so C is equal to 0, and A is equal to radius of the circle. So then eccentricity of the circle will be equal to 0. So it's some specific case of ellipse. Okay, so once we define the key features of the ellipse and elliptic orbit, we can proceed further with the second Kepler's law. So second Kepler's law, as you remember, it states that the radius vector from the sun to the planet sweeps out the equal areas in the same interval of time. So this comes, this second law, Kepler's law, which was again obtained only from observation of the planets with respect to stars. It comes from the fact that we have conservation of angular momentum. So let us consider this case in more details. So let's have a sun, and we have some elliptic orbit, not perfect, but it's okay. So here we have a planet with some mass. So we have this sun has some mass, ms. This is mp, mass of the planet. So there is only one force. It's in space, so there is only one force which acts between these bodies. It's the gravitational force. So the sun exerts some gravitational force on this planet. This is gravitational force, and this force is along the radius vector, so along the line which connects the sun and the planet, and directed towards the sun. So also our planet is moving along the axis and along this elliptic orbit, and it has some velocity, like linear velocity, which is directed tangentially to the trajectory. So this gravitational force, let us consider the torque which it creates on the planet with respect to the axis which goes through the sun. So perpendicular to the plane of our image. This torque will be equal to 0 because gravitational force is a centric force, and it goes, if we draw this axis of force action, it goes through the sun, and with respect to this point, which axis which goes through the sun, torque, as we defined on our previous discussions, will be equal to 0. So this is our torque equal to 0. Because in order it to be not equal to 0, it should have some force arm. But in this case, force arm is equal to 0 because our force is eccentric force, which goes to the axis towards the point where axis crosses this plane of the image. So we know from the law of conservation of momentum, that angular momentum, that the total external torque is equal to the change of the angular momentum over time. If this torque is equal to 0, because we have a closed system here, like isolated system, and there is only gravitational force which doesn't create any torque, then this derivative is equal to 0, and it means that angular momentum is constant. It doesn't change. So let us remind how we define the angular momentum of a particle which rotates about some axis. That was equal to the vector product of radius vector to the linear momentum vector. And this can be written as radius vector and cross or vector product to m of the planet, or we actually use capital. Let's delete this. mp, mass of the planet, and linear velocity of the planet. So since this is a constant, we can take it out from the vector product. mp r times v. Okay, so from the other side, we remember that we need to deal with this area which is swept off by the radius vector. So let us maybe go to another slide and draw another ellipse. So here is our sun, here is our planet. We have radius vector r. Then in some time interval delta t, this radius vector, we have some change in radius vector, which is dr, because our planet is moving. So from the area which is swept off by this radius vector r will be actually area of this triangular, like here. And this will be dA. So we can write that this dA is equal to the absolute value of vector product between radius vector and change of radius vector. Because you remember that absolute value of vector product is equal to the area of a parallelogram, which is formed by two vectors which we multiply. And this area of the dA is just half of this area of parallelogram. So that's why we write 1 divided by 2. Oops, sorry. Okay. 1 divided by 2. And it will be radius vector. Why it didn't stop? Excuse me, please. Who doesn't? Oh, finally. Okay, so this area, which is split by the radius vector r, delta dA, is equal 1 divided by 2 times to the absolute value. So we better take like modulus of the vector product of radius vector r and change of radius vector dr. And this is, we take absolute value. So now we can write further that it's equal to 1 divided by 2 r times, so dr is nothing else when dt is very small, change in time is nothing else as the product of velocity, linear velocity to dt. So we can write v linear velocity times dt. Now we can take factor out dt since it's a constant, and we have 1 divided by 2 absolute value of the vector product of radius vector and linear velocity dt. So this is very similar to what we wrote before for the angular momentum. On the previous slide, we wrote that angular momentum is the product of radius vector to velocity times mp, which is the mass of the planet. So from here, we can write that r times v, like absolute value of this vector product, will be equal to L. So here we don't have vector because we take the absolute value, angular momentum divided by mp. And now we can substitute it here. So as a result, dA is equal to 1 divided by 2 L divided by m, not this, capital M, ME times dt. So from here, we can write that dA over dt is equal to 1 divided by 2 L divided by mp. That means the derivative, it shows a change of the area. So the area which is swept out by the radius vector per unit time is a constant value, because this is constant. We showed it on the previous slide, since the gravitational force is eccentric force and it doesn't create any torque on the planet with respect to the axis axis of rotation which goes through the sun, and mass of the planet is also constant. So dA over dt is some constant value, which is actually mathematical formulation of the second law, Kepler's law, which we formulated in words, and now we just show based on the concept of conservation of momentum, angular momentum, that it originates from this concept. So we have some physical background of this law. At that point, as I mentioned already several times, it was just a result of many observations, and they were summarized and analyzed based on these many observations. Kepler came to this conclusion, but it definitely has some physical background behind it. Okay, so I guess next time, we are running out of time. Next time we will continue with the discussion of the third law, Kepler's law, and physics behind it, and proceed further in discussion of gravity. Okay, thank you very much for attention. Have a good evening and take care. See you on Wednesday.
Excuse me, Professor, can I ask one question? One quick
Sure.
question. What could happen if dA over dt would be equal to 0?
I mean, that will mean that the planet doesn't move, but yeah, it definitely not possible, but just from the mathematical point of view, it means that there is no change in area which is swept out by the radius vector, and that means that radius vector just stays in one position.
Okay, thank you.
But indeed, it just has some value, constant value, and that is because the further planet is located from the sun, the smaller is linear velocity. The radius vector is longer, but proportionally to the increase in radius vector, linear velocity is decreased. And in the contrary, when planet comes closer to the sun, radius vectors shortens, but linear velocity increases. And that's why when we consider the vector product of these two vectors, they cancel, the changes of radius vector and linear velocity cancel each other every time. And this area which is swept by the radius vector, which is half of the vector of the absolute value of the vector product of radius vector and velocity vectors, is a constant value. And this relationship between change of the radius vector and change in linear velocity originates from the concept of conservation of energy. Conservation of angular momentum.
Okay, thank you.
Okay, you're welcome. Good, guys. Then see you on Wednesday. We will continue.
Thank you. Bye.
Bye.
Goodbye.